Good morning, friends. Good morning, everyone. For those who have entered my channel, you'll be seeing a very good video on expression for SK velocity, which is being uploaded. And this is my first video which I am making into my channel. So, basically, I am an aerospace engineering master graduate, uh, and I want to share some of my knowledge and skills with you so that your knowledge can be improved, and I can also have a learning platform where I can educate all the students, those who aspire to become an aerospace professionals. So this is a derivation which we have already studied in our 10th or plus 2. So basically, this important derivation plays a major role in determining the exit velocities or escape velocity of any body from the Earth's surface. Normally, uh, we have our Earth, you know, having a radius. Let's say we have RE radius. So basically, when you throw a ball from the atmosphere to atmosphere, maybe within the Earth's surface, your intention is like, okay, let me throw this ball from Earth's surface to some infinite distance. Okay, so basically you have an idea. Okay, when you want to throw a ball from this point to this point, from infinite position, you definitely need a work done. Okay, so that should overcome the gravitational pull of the Earth. So in Earth we experience a gravitational pull that is called the uh, gravitational force, which we have already studied as per the Newton's law of gravitation. Okay, maybe, and if this is you and you are trying to throw a ball from here to you are from the Earth's surface, and now you are throwing from here to here again to the infinite position. Okay, okay. Now you tell me, okay, at what velocity I should throw this ball? Okay, so that it will escape from the Earth's gravitational pull. So that term is called your escape velocity. So escape velocity is a velocity which is required uh, to move an object from the move an object against Earth's gravitational pull and to reach at a specified infinite distance. So distance, this can be a orbital position, or it can be any unknown orbital path where it has to be inserted. Okay, now this is the path of the ball. Maybe from RE you are throwing from here to here to the infinite distance. So basically this is the overall picture of your escape velocity, and how to do this one, it's very interesting. So as I already told, you're standing on the Earth's surface. Okay, you're throwing the ball from this position to the infinite position, and with the help of some propulsive force, some work is being imparted to carry this object. Here it is the ball. Carry this ball from this point to this point at an infinite distance. Well, that is pretty interesting. So you require definitely a propulsion system that should carry your ball from this position to an infinite position. Okay. So basically, you're doing your work. So in your basic elementary school, you have studied. So if you have a block or something, and you are exhibiting some force. Okay. Now it is being moving at a distance, maybe at a small distance, maybe ds or something. Okay, so the energy which is being exhibited can be represented by du, which is equal to f dot ds. So this is basically your du is actually your energy, which is also equal to work done. Okay, so work done is equal to force times distance, maybe ds. So in this context, uh, if at all you are doing a work, then probably that should always have some energy also, because work done is also equal to energy as per work energy theorem, okay, which you have already studied. So I will give you a tip for you. When you have a force term, when you have some distance term, let's say dx, and if you are asked to find out the uh, energy experienced, then probably you can equate like this, f dot dx. So when you have the energy and when you have a dx term, you can definitely find the force again. It is basically the derivative of du by dx again. So these are some of the concepts which we should be very clear. Okay, coming back to here, now we are providing some work to make sure that you are throwing this ball from here to here. Okay, so let we call that work has to be W, and W should be a moving work done. Okay, that should be good enough to move this object from here. So basically, it is a kinetic energy which will make the ball to move from this position to this position. Okay, so that is your kinetic energy, and this kinetic energy should be sufficiently good enough to exhibit a good force or good energy against a gravitational force. So we have a gravitational force equation as uh, force which is given by Fg is equal to Gm m by r square. But we want energy term. Okay, to have a balance, you have an energy term. So as far as the your work energy theorem is concerned, when you have force term, when you have some position, let's say we are doing some work from this position dr, okay, from the here to here. So basically your dx is going to be changed to dr. Okay, so your expression will be like uh, f is equal to du by dr. So here u is actually the gravitational potential energy, and f is the gravitational energy, and dr is the elemental radius dr, which is a small distance which we have taken for integrating from this position to the infinite position. Now let's derive the gravitational energy, because we already have the work done equation, and now again we have a force equation, but we don't have energy equation. No, you just follow the basic rule. Your F is equal to du times dr, and from here you will get the gravitational energy, which is basically like du, which is equal to F dot dr. Okay, integral from, let's say, from 0, maybe from re to infinity. Okay, re to infinity. So this is basically the fundamental which I have already explained, because if you take f into dr, you'll get du. So if you have to get the total du, then you probably need to integrate from the concerned limit. So here it is from re to infinity, uh, which is the required limit. Okay, and we already know that. Okay, now let's make this equation as 2. So by doing the energy balance, we have W. Now I'll write here so that we'll get some space. W is equal to integral from re to infinity f dot dr. Okay, so basically it should be greater than or equal to, your work done should be greater than or equal to the gravitational energy. Okay, so this is the work done, and this is your gravitational potential energy. Okay, gravitational potential energy. So this should be against the work done should be against the gravitational potential energy. So you always put a minus sign over here, which is a bit relevant. Okay, because you're providing a work which is against the earth gravitational potential energy, so definitely we are going to get a minus sign over here. Okay, so that is a good concept again. Now we know that work which is being the kinetic energy. So now let's write down the equation for kinetic energy, which is f mv square, which is equal to minus integral re to infinity f dot dr. Now F is something like, we know the gravitational force, uh, which is given by the Newton's law of gravitation again. So we write half mv square. We write half mv square is equal to uh, gm m by r square from the integral from 0 to RE to infinity, and you put a minus sign over here because the work is done against the gravitational potential energy. Now your m and m gets cancelled off, and here you sorry this is something you have to be very careful. Okay, you have to write like this because only gm term is the constant term, and m again gets cancelled off, and dr by r square, which is the inside of the integral. Okay, now you can write v square by 2, which is equal to g minus of gm into, when you integrate this term, this is basically integration of uh, dx by x square. Okay, so it's basically like integral x power n plus 1 by n minus n plus, yeah, integral x plus n x raised to n plus 1 divided by n plus 1 again. So here the power is minus 2, so once you integrate you will get something just like this, minus 2 plus 1 divided by minus 2 plus 1 again. Okay, from the limit ra to infinity. So again, if you do some substitution again, okay, now you are going to get some good expression which is called v square by 2, which is equal to gm by re. Okay, now you have this final expression of gm by re. Now let's say you take this 2 here, so v square is equal to 2 into gm divided by re. Now v is equal to, you can write v is equal to, maybe my work may be shabby, but my intention is you will be having a good knowledge on this once you learn about the work which I have done right now. So v is equal to 2 into gm divided by ra. Now in space dynamics we always denote gm as maybe gm is equal to mu, so your expression again tends to be v is equal to under root of 2 mu by re. Now this is a basic equation of your escape velocity of any body from the earth. Okay, so re can be even, in fact, from the maybe from the above the earth surface. So if re is having a little bit of more about the height, so probably re plus h term will also come over here, and we need to make the suitable approximation, but basically the idea remains the same. So once we have the escape velocity for any planet, then probably you can design any propulsive vehicles accordingly. So uh, your mu values actually depends upon the planet mass, and g is the gravitational constant, because mu is actually a product of g into m, which is we already know. Okay, so g is a gravitational constant, m is a mass of the earth, so it will having a finite value which you can find out from the relevant data book, and r is actually your radius of the earth, so your escape speed is equal to 2 into mu by re. So here you need to know one term. If you write root 2 into root of mu by re, then probably this term, okay, this term is also called as the orbital speed or orbital velocity, okay, of the earth. That means how much the earth is orbiting around in a path, or in a elliptical orbit, or it can be a circular orbit. So basically what is the orbital speed which is being exhibited by the earth, that is called the orbital velocity, which is again a constant term. So you can write again your v escape should be equal to rooted to 2 times of v orbital, vor we can write. So this comes around by 11.2 kilometers per second. Okay, so now we got the final expression for v escape is rotated times v orbit, which is equal to root of 2 mu by re, where mu is the gravitational parameter. Okay, gravitational parameter. So hope this video is very informative for the aspirants for aerospace engineering. So I'll try to cover some more short videos where you can explore and you can have a good knowledge on how the orbital mechanics is being carried out by different propulsive vehicles, and how the planets have been experiencing the gravitational force, and how the mass can be or an object of mass of m can be uh, lifted from a Earth surface to a different planetary orbits. So this is a bit interesting video. So I'll also try to cover some of the aerospace engineering subject oriented videos as well. So being a first video, I just want to make sure that this has been conveyed properly. Okay. So thank you so much. Thank you for your time. So have a great day.